Okay, welcome back. This is the second portion of the first lesson of the equilibrium unit, where we're going to look at how to write an equilibrium expression and then solve for equilibrium constants. So an equilibrium expression is the same thing really as a mass action expression, where it gives ratios between products and reactants raised to the exponent equivalent to their coefficient from the balance equation. So this section here I cut off of your reference sheet. Your reference sheet for equilibrium has a ton of equations on it, so this is just the portions that we're going to look at right now. So it shows you how to write a Kc expression, a Kp expression, which is really the same exact format, and it tells you what Kc and what Kp mean. So if it just says Kc, that has to do with molar concentrations. If it's Kp, that means you're working with gas pressures. So this example question, write the equilibrium expression for this reaction. We'll write the Kc, so it's capital Kc, and we're going to take products over reactants, and we're going to raise them to the power of their exponents. So the products would be the NO, so concentration of NO, that would be squared, times the concentration of oxygen over the concentration of NO2 squared. So that's how you'd write a Kc expression. If you wanted to write this in the form of a Kp expression, it would be explicit in a question. It would say Kp or Kc. You'd do Kp equals the pressure of NO squared times the pressure of O2 divided by the pressure of NO2 squared. You have to be really clear about that. This is just the same thing here. So pressure is proportional to concentration for gases in a closed system, because you can calculate moles over liters for the gas to get a molarity as well as calculating a pressure. It's the same exact kind of expression. So just make sure you're clear, whatever the question's asking, that you address it properly when you write your pressure expression, and it can only include gases. These two values don't have to be the same. They would be the same if the number of moles of gases on each side is equal to one another. So here's an it's another example, Kp and Kc. So the Kp expression, these are all gases, so they're all going to be included. So it'll be the pressure of ammonia, the product, squared, divided by the pressure of nitrogen, and that would be to the first power, times the pressure of hydrogen, and that would be cubed. The Kc expression would be concentration of ammonia squared over concentration of nitrogen times concentration of hydrogen cubed. Here's when we're going to calculate the value of Kp based on pressures that are given. So this is the pressure at equilibrium of each of the three substances. So the first thing we're going to do is write the Kp expression. Kp equals pressure of ammonia, and that would be squared over pressure of nitrogen times pressure of hydrogen cubed. So now we just plug in our numbers. The pressure of the ammonia is 0.029 atmospheres, and we're going to square that. The pressure of the nitrogen is 0.89 atmospheres, and then the pressure of the hydrogen is 0.0029, and that would be cubed. So when you plug this into the calculator and solve, I got 38,745. So these numbers can have a huge range. You could have 10 to like the negative 30th power. You could have 10 to the 80th power for the exponents for these. So it's really spread out. So here, the Kp of the reaction is 1.05. Find the pressure of chlorine if the pressure of PCl5 is 0.875. PCl3 is 0.463 at equilibrium. So it's just, again, you're solving algebraically. So we'll write the Kp expression. So Kp is equal to the pressure of PCl3 times the pressure of Cl2 over the pressure of PCl5. So now we'll substitute in the numbers that we have. So Kp is 1.05. The pressure of PCl3 is 0.463. Pressure of chlorine is our unknown, and the pressure of PCl5 is 0.875. So when you cross multiply and then solve by dividing by 0.463, I got 1.98, and that would be in atmospheres because we're looking for the pressure of chlorine. So when you're dealing with these equilibrium constants, make sure you capitalize the K. And something else about K, it is a constant, so it's going to be the same number at a given temperature. So temperature will affect the value of K, which we will discuss in class. So it doesn't matter the amount of reactants or products that are present initially. Once you establish equilibrium, K value will end up being the same throughout. And then here, for a reaction at a given temperature, there are many positions for K, for equilibrium, but there's only one mathematical value for K. So here's the idea behind equilibrium position. So that would mean, at equilibrium, do I have more reactants present? Do I have more products present? Or do I have approximately equal amounts of both? Because remember, at equilibrium, you don't need to have equal concentrations of reactants and products. The concentrations just have to be maintained while the system's at equilibrium. So when a system reaches equilibrium, there may be more reactants or products present depending on the conditions of the system. So the factors that would influence, which quantity would be more, which quantity would be less, would be something like the initial concentrations of reactants or products present. If you have a lot of reactants present initially, that forward reaction can occur rapidly. It also has to do with the relative energies of reactants and products, whether reaction is endo or exothermic, and also the changes in entropy that are occurring as well. So this diagram here has to do with equilibrium position. So if you have an equilibrium where products are favored, that would be indicated by a large value for K. So large means that if K is greater than 1. So if K is greater than 1, when you're at equilibrium, the concentrations of products would be greater than the concentrations of reactants. So that makes sense because K is equal to product concentrations over reactant concentrations. So if at equilibrium you have a high number of products, then your numerator is going to be larger and your K value is going to be greater than 1. Oppositely, if you have a small value for K, that means when you're at equilibrium, you have a lot of reactants still present. The forward reaction hasn't really occurred, hasn't occurred to much extent, and so when they balance out, the reactants will be present in a greater amount. So again, this makes sense because equilibrium constant is product over reactants. So if you have a lot of reactants present at equilibrium, mathematically the denominator is larger, so that would mean your K value would be small. So if your K value is less than 1, it's reactant favored. If your K value is equal to 1, that means that the reactant concentration and the product concentrations are pretty much going to be equal. So to summarize, if your equilibrium lies to the right, it's product favored, the value for Kc is greater than 1. If it lies to the left, that means it's reactant favored. So product favored and reactant favored. So if it's reactant favored, the value for K would be less than 1. So based on the first video and this one, you should be able to explain what chemical equilibrium is. You should be able to write a mass action expression or write an equilibrium expression. And you should also be able to calculate concentrations or pressures of species in a chemical equilibrium reaction.